We will be looking at some basic graph models. First, starting with the different ways to represent graphs in Matlab. The first example we're going to be looking at is a complete bipartite directed graph. Directed graphs are sometimes called digraphs, as an abbreviation for directed graphs. A bipartite graph is a graph where all of the nodes in the graph are separated into two different sets of nodes. And in a logistics context, the bipartite typically represents each set of nodes represents a different level in a logistics network. And then the arcs connecting one level to another are directed because the flow of material or product in the logistics network is only from one level to another. A classic example would be from suppliers to customers. And then this example shown in the slide is an example of a complete graph, and a complete just means that there are arcs from each node in one level to all of the other nodes in the other level. And again, in a logistics context, that just means that each supplier can serve all of the customers, for example, in the next level. And in this example, the arc connecting node 2 and level 1, say for example a supplier, to customer 4, represented as node 4, is shown as a value of 0. And that could well represent the case where the supplier is actually located at the customer's location. It may be the same manufacturing facility, so the supplier and the customer are the same entity. So in this case, there are no transportation costs, so we do want to represent 0. Unfortunately, in Matlab, when we try to apply different graph representations, the value of 0 and the value of 0 indicates that there's no arc connecting the two different entities. So we have a problem. The reason that it's done that way in Matlab is that it's typically convenient to represent adjacency matrix, which are one of the most common ways of representing graphs in Matlab. It's common to represent adjacency matrix using sparse matrices, where most of the values in a sparse matrix are not represented, and by default they're assumed to have a value of 0. And for many adjacency matrix, they're not complete, so there are not arcs connecting every node to every other node. Most of the pairs of nodes in an adjacency matrix are typically not represented with an arc connection. So because of the prevalence of 0, we have a problem when in the logistics context we want to explicitly represent that 0. So one way that can be done that is accommodated within Matlog, not Matlab in general, this is just a Matlog way of representing 0, is to use in the interlevel matrix C the not a number sign, and that's going to indicate that it really shouldn't be a 0. If we put a 0 in the interlevel matrix, then we would be representing that there's no arc between that pair of nodes in each level. And in that case, it wouldn't be a complete network. But in this case, we want to explicitly represent the fact that it really is a 0. So putting a not a number there, and then when we display it in Matlab and using the mDisplay function, not a number and also infinities are not displayed. So we have just an empty cell in this matrix display. And then when we use the matlog function to convert an interlevel matrix to an adjacency matrix, we end up with a 5x5 adjacency matrix. The interlevel matrix, we have 3 nodes on one level, 2 nodes on another level, so it's a 3x2 matrix. The total number of nodes is 3 plus 2 or 5. So adjacency matrices are represented as a square matrices where the number of rows and columns represent the number of nodes. And then the value in the matrix represents the value or cost of the arc. And all of the zeros represent the fact that there are no arcs. And the only possible arcs are this upper portion of the adjacency matrix, this 3 by 2 portion that represents the interlevel matrix. Everything else is 0. And in this case, the not a number is carried over into the adjacency matrix. The functions in Matlab itself, if we're using Matlab functions that are not part of Matlog, the not a number won't be represented or interpreted as a 0. But if we use any of the graph or network functions in Matlog, then the not a number is interpreted as 0. Just keep in mind that that's a Matlog convention, not a more general MATLAB convention. I guess I would argue that it would be nice if MATLAB would actually honor that convention, because I think it is convenient. But just keep in mind that this is something that's not going to be part of MATLAB in general, if you're using it starting with the Matlog component. Then we can, in this case, we've added 2 arcs. So now it's just a bipartite graph. And we've added an arc from node 4, one of the customer nodes, back to the first supplier. And we have a 3 here. So now we have a bipartite graph. Bipartite graphs are, in this case, not directed graphs. So what's different about this relative to the first is now we have an arc that is not directed, going from nodes 1 to 4. It has a value of 6. So in terms of being able to represent that value, we are using another representation. And in this case, this representation is called the arc list representation. And we can convert an adjacency matrix to an arc list representation by using the adjacency to arc list function. When you look at the resulting arc list, you can see that the undirected arc is represented twice in this representation. So we have a 4 to 1 and then a 1 to 4. Both have the value of 6. Also, from 2 to 4, which is our directed arc that has a 0 cost, that is actually represented as a value of 0 in the arc list. So the not a number that we had put originally up here in the interlevel matrix now is carried over into the arc list representation as a 0 value, which is, from the application point of view, what we want it to do. One of the things we've done here is we've made the arc from 3 to 4. We've essentially eliminated that arc, and we eliminated it by setting its value in the adjacency matrix to 0. And instead of the not a number shown here, the 3 to 4 now here is shown as a 0 value. But then when we converted the adjacency to an arc list, that 0 is not shown in the list, because that 0 represents the absence of an arc, whereas the not a number is actually represented as a 0. So in terms of that figure, we have a total of 7 arcs, and 7 because the arc from 1 to 4 is represented twice. It would be convenient if we could just have it represented as only 6 rows in this arc list representation, and we can do that by convention by representing in an arc list undirected arc by specifying in the second column for the j or origin of the arc a negative value. So in this case we would have 4 minus 1, 6, and then that would eliminate the need for this to be repeated twice. Or we could have 1 minus 4, 6, and then the 4, 1, 6 would not be repeated. So that minus in the j column, which is the second column of the arc list, is used to represent that. So in the next example, we have a multigraph, and here I'm going to explicitly generate my arc list, and here I'm using the minus sign convention. And in this case, it's a multigraph because I have 2 undirected arcs between nodes 1 and 4. The first one has a value 6. The second one has a value 18. When we look at the adjacency matrix and look in this 1, 4 column, and it's symmetric, so we have a 4, 1 has the same value, those values are 24, which is the sum of the 6 and the 18. So Matlab, when you try to create, and we're using essentially the sparse function, and we're creating a sparse matrix, and using the sparse function, when you create the same element more than once in a sparse, calling the sparse command, it adds up whatever you're specifying. So that's the default Matlab behavior. Unfortunately, for most logistics applications, adding up the values is probably not what you're trying to represent. In this case, for example, the 18, which is the higher cost, might represent maybe a more costly mode of transport, and then the 6 is a less costly, but the 6 maybe has some limited capacity, so you can only use so much of the cheaper transportation, and then beyond a certain quantity of flow you need to specify using the higher cost arc. And to do that, you'd have to include lower bounds and upper bounds on the arcs, which we'll talk about in a minute as how we can actually represent that. So there are contexts where a multigraph is something we do want to represent. The important thing to remember is that when we do that, we need to just use the arc list representation, and we cannot represent it using the adjacency matrix. So that's one of the reasons why it's convenient to have multiple different types of graph representations, because depending on what we're wanting to represent, some are not able to represent, like in the case of the adjacency matrix, or in other cases, one representation is just more convenient than the other representation. So in some cases, an adjacency is more convenient than an arc list, even though we can't represent everything. So having multiple ways of representing graphs is very convenient, and a lot of the functions that work on graphs in Matlab are the ones that convert from one representation to another. And by convention, we use the number 2 to indicate those transforming functions that take one representation and convert to another representation. The next example is a complete multipartite directed graph. And for this example, I'm going to copy the original interlevel matrix, and I'm going to label it 1, 2. And then I'm going to add a third level. And that third level, I'm going to take the nodes in the second level of the original and then indicate the connections from that second to the third level. And I'm going to call that interlevel matrix C23. So now I have these two different interlevel matrices. They both share the second level. Those two nodes in the first are represented as the two columns, and in the second they're represented as the two rows of this matrix. When we want to convert both of those into an adjacency matrix, we can use the level to adjacency function with 2 input arguments, and we get the corresponding adjacency matrix. This is particularly important where we have multiple levels, in more than 2 levels in a logistics network, maybe a supplier level. The next level could be distribution centers, and then maybe a third level would be customer levels. And being able to do it all in one application is convenient. The restrictions are that the number of columns in the first have to match the number of rows in the second to be able to make a complete connection. The next example is looking at the transportation problem. And the transportation problem is a generalization of the allocation that we've looked at for the ALA procedure. And the difference is that previously we were essentially by default assuming that we had infinite supply for any of the new facilities that we were allocating, or any of the new facilities that were serving customers as existing facilities. In the cases where the new facilities are not of infinite capacity, where they have some finite capacity, it can be the case that we're not able to allocate everything that one existing facility requires using just a single new facility. Because of a capacity restriction, we may have to serve it from more than one. So being able to explicitly represent the limited supply is an important feature of many applications. In logistics, it's typically the case where some of the new facilities are actually existing facilities, so they have fixed location, and then since they're already built, they also have fixed capacity. And then those, together with maybe some new facilities that can be located anywhere and also can be constructed to have any capacity, that would fit the ALA examples that we had talked about previously. But in this case, we need to have a restricted type of allocation, and we can do that using the problem and modeling it as a transportation problem. So example 3 for the ALA procedure shows a case where we have constrained new facilities, where each new facility can handle a third of the total demand. And we can represent that as a transportation problem. So I'll get back to that after we talk first about the transportation problem. So for a transportation problem, if we wanted to do the case where we do have infinite supply, I'm going to use as an example the case where we have 3 supply nodes serving 4 customer nodes, and that's a 3x4 interlevel matrix. And in the case of infinite supply, we can easily solve what is the optimal solution by just taking the minimum elements in each column of the C matrix. So we get the first 3 customers are served by facility 1, and then the 4th customer is served by facility 3, and then facility 2 does not serving any of the 4 because it's not the lowest cost alternative for any of the 4 customers. And in the case then where we have an explicit amount of demand, before by doing the argmin, we didn't really matter what the demand is since we had infinite supply. But now when we have less than infinite supply, we want to specify the demand so that we know if a new facility has enough supply to actually provide. So in the case of infinite supply, we can convert the C matrix, which represents all of the interlevel cost, and then it's typically going to be convenient to be able to represent the total cost, to be able to represent the actual amount that's going to be flowing across the arcs in the network. So the way I'm doing that is I'm using the sparse function, and then I'm using the argmin to get my allocations to indicate what row the flow is going to appear in, and then I'm going to have the flows in all of the columns, so 1 to the length of the demand vector, and then the amount that's going to be flowed is just the demand. And all of that then is originally a sparse matrix, so I'm converting it into a full matrix and assigning it to the matrix F, which is a 3x4 matrix. What's convenient then is I can take that, multiply element by element the C's and the F's, and then the zeros that are in the F zero out the cost. So if I want to get the total cost, I can just sum up all the rows and columns and end up with a total cost of 930. So that's my cost where I have infinite supply, where there are no restrictions relative to the cost. And again, if I had infinite supply, I'd like the first new facility to be able to supply 95 units of flow and 30 for the third and 0 for the second. If I restrict the amount, so now the first facility, instead of being able to do 95, can only supply 55, the second can do 50, and then the third can do 40. So the third one can still provide the 30, but the only one that is restricted is the first. A good thing is to check the feasibility. In this case, it comes back as true, meaning that we have enough total supply that we can supply all of the required demand. And then we can expand the C matrix, the interlevel matrix, to include both the demands as a 4th row and then the supplies as a 5th column. This is a convenient or very conventional way of representing the transportation problem by adding the row and column to the matrix. And then one way of actually solving this is to use the greedy procedure, which we talked about in class, as compared to actually solving it optimally. When we apply the greedy procedure, there's a function in Matlab called gtrans, where you supply the interlevel C matrix and then the supply vector and the demand vector, and it returns then the flow matrix and the cost. And we showed up here how those are actually calculated. So all that's going on once the solution is found is it's converting it to an F matrix and then calculating this total cost. When we do that, it gives us a solution, and then because of the constraints, instead of getting a cost of 930, our cost is increased to 1030, and then this represents the total available flows. And we can see here, if we add up the first column of flows, we have a total of 55, which represents the total available supply. So that now is a binding constraint. Notice that when we execute greedy trans, we get a warning telling us it doesn't necessarily give us the optimal answer. It says instead actually use the trans function that is also part of Matlab. So using the trans function, we would get a better solution. We would actually get the optimal solution. So to see what that optimal solution would be, I can go back and instead of calling gtrans, just get rid of the G. And now I get a value of 970. That 970 value is still greater than the 930, but it's less than the 1030. And again, just to look at the feasibility of it, we can again add up the elements in the first row, and we get 5, 20, and 30, which again adds up to 55. And in this solution, again, the second node is serving 40, but it's providing it all to the first customer. And then this is something, again, using just a greedy procedure, which does, it's called greedy because it's always just doing the best thing it can do at each step. It doesn't, in this case, necessarily need a lead to the overall best solution. The next example that we're going to talk about looks at the min-cost network flow problem. And we're going to start off in the case of having no arc or node bounds, but in general we can add upper and lower bounds both to the arcs and to the nodes. And an example of the use of that would be, as we talked about in the multigraph case, where we want to have maybe an upper bound on the amount that we can flow across a low-cost node, and then beyond that we have to use the higher cost node. So the example network that we're going to show in this case has a total of 5 nodes. We can represent it as an arc list IJC matrix. And notice these are all directed arcs. There's no minuses in the second column. And then the other information is the net node supply, and that's indicated as a single vector S. And positive values indicate supply available at the node. Negative values represent the amount demanded at a node. And then zeros represent transshipment nodes that have no net supply or demand requirements. Everything just flows across them. So that's the second thing. And then to solve this problem, we can directly solve it as a linear program. In Matlab, there's a lplog function. And there's also a linear program that's part of Matlab's optimization. That's the one that you should use in general. This is one that was developed in case you don't have access to the optimization toolbox, and it was one developed in Matlab. So its performance is not as high quality as the one in the optimization toolbox, but it can be used to solve linear programs. So for this one, the way that we can solve it is first to convert the arcless representation to another type of network representation called an incidence matrix. And an incidence matrix, which let me go ahead and first create it so you can see an example, has the number of columns corresponding to the number of arcs in the network, but the number of rows corresponds to the number of nodes. And then in the incidence matrix, there's a +1 for the origin and a -1 for the destination of each arc. That's one of the reasons in the arc list that we use a minus sign, It sort of follows this incidence matrix way of representing the destination of an arc. And that represents in linear programming, this incidence matrix represents the A matrix that can be used directly in a linear programming representation of a network. And then the net node supplies are going to be the right-hand side. And these are defined as A, and I'm using EQ to represent constraints that are going to be equality constraints. And then for the network representation of the min-cost network flow problem, we don't have any less than constraints. So the first two arguments, which would be any constraints that are less than constraints, would be represented, both the A matrix and the B right-hand side. All we have are equality. So I can solve this, and I get a result saying, warning, row 5 is redundant. And I get this solution. I'm basically not able to actually solve the problem because I have one extra row. So what I'm going to do here is set that last row, and you could pick any row to remove. So I can remove it and also remove the corresponding right-hand side element. So now the equality, instead of being a 5 by 6, if you look over here, it's actually only a 4 by 6. So I've gotten rid of that redundancy. And that's true for any representation of a network. It's going to essentially be a redundant set of equations. So you need to eliminate one of the rows to make it so that it can actually be solved. And when we do this, we end up with a solution, a total cost of 34. And the output flag of 1 means we got a good solution. There's some other information output. This represents the indices of which columns of the incidence matrix form the linear programming basis. And then these are some of the dual variables, and so that this is additional linear programming information that most of the time you don't really need to utilize. We can also convert the min-cost network flow representation, which in the context of Matlab is going to be represented as the arc list and the net node supply. And we can assign that to a output, and what we get as an output is a cell array, a 7-element cell array, and those 7 elements represent the elements of a linear program. To see what those correspond to, we can highlight this. So these are all the elements, and then when we call the LP log, it essentially gives us the same solution that we had before. So all we're doing is taking advantage of the fact that the arc list and the net node supplies, those 2 elements are enough to represent the min-cost network flow problem directly, and then we can convert it to an LP and then use it directly to solve it as an LP. We can also take the LP representation and convert it back to a min-cost network flow. And when we do that, we get this value. And what is particularly useful about this is that whereas here, when we solved it as a linear program, we got as a first output argument just the variables x representing the solution of the problem. But in the case of a network flow, it didn't give us any context as with respect to what it actually represented. When we convert it to a min-cost network flow, it assigns it to this vector f, which indicates that it represents a flow of flow on the network, and also it gives us as a third output argument NF, which is the node flow. So this tells us how much flow is occurring across each node, in addition to the flow that occurs across the arcs in the network. And for several logistics applications, that information is useful. So here we're taking a general linear programming solution and converting it to a min-cost network flow. It's the same data, but it's presented in a more useful format. We can also use the linear programming function that's part of Matlab to solve, and we get the same result as before, and then we can do the same type of conversion. We can also solve it as a linear programming problem using the MILP object that's part of Matlab. We can use Groby to solve, and we can do that first clear in case there's any instances of the math programming model. And then we're going to create a brand new instance using the MILP model. And we're going to use one of the methods which converts the linear programming inputs to a mixed integer linear programming model instance. And then since we have a mixed integer linear programming model instance, we can then use another method that converts that to a Groby instance. And now we have the model represented as a Groby input, and then we can solve and get the same result where our total cost is 34. The next example looks at the min-cost network flow problem with bounds on the arcs and on the nodes. And also we can add cost to the nodes. The arc list representation, which originally had 3 columns, we can include the upper and lower bounds by adding a 4th and a 5th column. And by default, the upper bounds are infinity. By default, the lower bounds are 0. And in that case, we wouldn't need to include the 4th or 5th columns if we're using just the default values. But when we have anything less than infinity for an upper bound, we can include it as a element in the 4th column. And then likewise for the lower bounds, anything greater than 0, we can include as a lower bound for the arcs. So we're adding a 4th and a 5th column. The reason that the upper bound is 4th and the lower bound is actually at the last is that it's more often the case that the lower bound's default value of 0 is what we want for a problem. It's less likely that we have non-zero lower bounds. So in that case, if we would specify just 4 columns, then by default the lower bounds would be 0. We can do the same for the nodes, and here the original vector that just had the net node supply, what's been added first is a column of node cost as a second column, and then a third column is the upper bound on the amount of flow that can go across the node, and the 4th column is a lower bound. In the case of the nodes representing a production facility, the upper bounds would represent the capacity of the facility, and the lower bound, a non-zero lower bound, might indicate the fact that at least for some period of time the facility has to be producing a certain quantity, so there's not an option of having 0 flow across a node. In the case of the node representing part of a transportation network, then the capacity could represent just the physical capacity for transportation, transshipment that is available at that facility. So we can add all of this. And then to actually then create a problem that can be solved as a linear program, we can use the function MCNF2LP, which converts the min-cost network flow representation to the parameters needed to solve as a linear program. There are 2 inputs, the arc list and the node list. So with those we can generate the list of LP parameters and then solve it using LP log to get these results. And notice that unlike the case of not having any arc and node constraints and not having any node cost, our costs have increased. In the first case, because of the additional constraints, has forced us away from the previous solution. And then in the case of adding cost to utilize the nodes, that's a further reason that the costs have increased. And then if we want to look at the results not as the output of a linear program, which for example has no information about anything with respect to the nodes, everything is listed with respect to the arcs in the problem, we can instead look at it as a more network-focused representation by taking the LP solution, which is just the X output from the LP together with the 2 arc and node list, and then it can then converts it into a format that's more convenient. Again, it's the same information, it's just reconverted into a more familiar format. For example, here we have a total of 6 flows for the 6 original arcs. For the LP solution, there are more than that, and those additional arcs are the ones that are added with the dummy nodes that are added whenever we have constraints on the nodes or cost on the nodes. And the only way that that is modeled is by adding additional dummy nodes. And for those dummy nodes, they have additional arcs associated with those. And that's what's output for the LP. And unfortunately, unless you actually know where the dummy nodes are, it's hard to interpret what all this results represent. So I guess I could say that in some sense, this is really not useful information. So it needs to be converted back into a form that now makes sense with respect to the way we've represented the problem as a network. So we have the flows on the 6 arcs. Again, we have the same cost, that hasn't changed, but also there are 5 non-dummy nodes in the original network, and for those we know the flow across each of those nodes in the optimal solution, and that's additional information that's represented here. To be able to display the results, I'm going to convert the LP parameters into a mixed integer linear programming representation, just so I can use the display model method. First, I'm going to take the original LP parameters that were created that don't have the additional bounds and node cost to get an idea of what the original linear programming model looked like. Here we have a total of 4 constraints and 6 columns representing the 6 arcs in the original matrix. And then LP2 represents the expanded network that includes the dummy arcs. And you can see for that there are the additional arcs and the additional constraints added to the model. So again, this is the one that would be hard to interpret. This one still is close to what the original representation of the network was. Okay. Next, we're going to solve the transportation problem as a 2-level min-cost network flow procedure. And this is what is sort of happening inside of the trans function. It's taking the representation of the problem as a transportation problem, which is essentially just the interlevel matrix C together with the supply and demand, and then converting it into a min-cost network flow. So the first step is to create the adjacency matrix, convert that to an arc list representation, and then to take the supply and demands and then turn it into a net node supply vector by taking a negative of the demands. And then we can solve it by first converting to a linear program, and then we're solving the linear programming problem. We get our result, 970, and then convert that back into a representation that corresponds to the min-cost network flow version of the problem. And then instead of stopping at that point where we just had this vector of flows, we would really like to be able to get back the original matrix, a 3x4 matrix, F representing the flows. And we can do that, sort of, I guess a trick to do that is to start with our original arc list representation and then only take the first 2 columns. The third column represents the arc cost, and now what we're wanting to do is replace those costs with the flows. So I'm going to redefine an IJF arc flow matrix as the first 2 columns of the IJC, which represent the arc beginning and ending points, and then replace cost with the flow. And then I can use the arc list to adjacency representation. Notice that all of the zeros that were in the arc list are replaced with not a number because they really are 0. And then the arc flow representation can be converted into the flow matrix by using the adjacency to interlevel or ADJ to LEV function. So we get back our underlying flow matrix. And then from that, we can multiply times the cost elements and then double sum to recreate the 970. So essentially, all of this code, these 3 cells of code, represent what is sort of under the hood in the Matlab trans function. And I think you can argue that it's a lot easier to work with the transportation problem, a representation where we just had the C matrix and the demand and the supply information, and not have to worry about doing all of this. You know, if we're going to be repeatedly solving a transportation problem, then it's not convenient to have to do all of this work. We can also solve this as a transportation problem that involves an additional middle third level, and that would be a transshipment problem. As a transshipment problem, we can take the original C matrix, assign that to the represent the arcs from the second to the third level, and then add some additional arcs from a first to the second. So the original problem was a 3 to 4. Now we have a 2 to 3 and then a 3 to a 4. And then we can use the level 2 adjacency to create the underlying adjacency matrix, convert that to an arc list representation. And then for this one, we're going to create the net node supply by using as a supply the values 65 and 80 for the 2 new nodes in level 1. And then for the 3 original supply nodes, we're going to make those transshipment nodes. And this is the second or middle level in this 3-level problem. And these have a net flow of 0, so they're transshipment nodes. And then we have the original demands, which are negative net node supplies. So that's our net node supply vector. We can then convert that into the arguments needed to solve as an LP. We can solve as an LP, convert it back into the min-cost network flow problem elements. And then finally, for the report level, we can do just like we did before, create an arc flow representation. And then this is a adjacency matrix corresponding to this. And then in terms of being able to convert the adjacency matrix into interlevel matrices, one way you may think would work would be to take, say, for the example, the ultimate size of the F matrix that we had before, which is a 3 by 4. And if we tried to do that, we would get an error because the output has to correspond to the multiple levels of the interlevel matrices. We could also try doing the number of nodes in each level, 2, 3, and 4. And if we do that, we have the input arguments correct. We basically specify the dimensions of each of the 3 levels, and we include the adjacency matrix. What we don't have right is that we only have one output argument, and it can't assign that. Essentially, what we want is to assign 2 output arguments. The first are the flows from level 1 to 2, and then the second is the flow from level 2 to 3. So the first is a 2 by 3 and then a 3 by 4. And with those with that, we can then display the underlying information in terms of the cost. Same thing we do here where we specify these 2 input arguments.